All right, this is the Unit 3 practice exam. Questions 1, 2, 3, and 4. These are from section 4.1 and 4.2, solving a triangle using law of sines or law of cosines. So first decision you would need to make on each of these 4 questions is which law applies. Are we going to use law of sines? We're going to use law of cosines. That depends on what type of triangle has been given or which parts of the triangle have been given. For those that have a hard time visualizing just based off the description, really isn't a bad idea just to draw a random triangle. That's not, there we go. And label A, B, and C. According to the information, angle A is 102 degrees, angle B is 34 degrees. And then side A, which is opposite angle A, would be 7. So what we need to do is find angle C, side B, and side C. But going back here, what we've been given is angle side, and angle side is going to be a law of sines. So luckily you'll have this formula sheet on the exam as well, and law of sines are given right there. Let's do the low-hanging fruit here. This missing angle will be the easiest one to find first, since we already have 2 of the angles. So if we add, we get 136. Then if we subtract that from 180, we get 44. So we know that angle C is 44 degrees. Or the measure of angle C, rather. So now we need to find the length of side, let's see, C, and the length of side B. Let's start with side B. So side B over sine B is equal to, let's do length A since we know it. And we already know actually angle B, so I'm going to, instead of writing B, I'm going to write actual angle there. So angle B was 34 degrees, and then side A is 7 degrees, and the sine of A is 102. So getting B by itself, we'd have to multiply both sides of the equation by sine 34. So B is equal to 7 times the sine of 34 divided by the sine of 102. So we need a calculator now. 7 times the sine of 32 actually, it was 34. Let's try that again. 7 times the sine of 34, and then we need to divide that by the sine 102, and that's pretty close to 4. So measure of side B is 4 meters. Now we're going to do a similar thing here to find side C. So side C over sine of angle C, and I'm going to use A over sine of angle A. And if we multiply both sides by sine of 44, So we need 7 times the sine of 44, and then divided by that, by the sine, 4.97. So angle C is 4.97. Those measurements are found using law of sines, because what we had given originally was a angle side triangle. Now question 2, we have angle A, which is 88.1. We don't know angle B or angle C, but we know that side C is 8.6 inches, and we know that side B is 14.5 inches. So what we have here is an example of side angle side. Side angle side is going to be law of cosines, and if you're having trouble remembering which one applies, law of sines or law of cosines, if you try to apply law of sines to this one, so if we use this ratio, A over sine A, we know sine A, so we could replace that with angle 88.1 but we don't know any other angle. So if we try to use another ratio like side B, which is 14.5, there's 2 unknowns, so we can't solve that equation. So we could try it for C. Side C is 8.6, but we don't know angle C either. So there's 2 unknowns, so that one's not going to work. So law of sines isn't going to work. It has to be law of cosines. And let's see. Law of cosines, there's 3 versions of it. And we only know one of the angles. We only know angle A. So we can use, we got to decide which version of this to use. So if we want to solve for A squared, or for side A, for example, we have to know side B, we have to know side C, and we have to know angle A, which we do. So we can use this form of it to solve for angle A. So it's A squared equals B squared plus C squared minus 2BC cosine A. So this is 14.5 squared, 8.6 squared, and then we need to multiply that times cosine of 88.1. We have 14.5 squared plus 8.6 squared minus 2 times 14.5 times 8.6 times the cosine of 88.1. So it's 275.94. If we square root both sides, So the square root of that previous answer, 275.94, is 16.61. And we are, what unit of measure are we in? We're in inches. So we found that missing side using law of cosines. Now we have three sides and an angle. So we need to find the other two angles. And since we're already on law of cosines, just stick with it. If we want to find angle B, for example, let's go back to law of cosines formula sheet. If I want to find angle B, then we could use this version, or that version there just has the formula rearranged so that cosine B is already isolated. So it's a squared plus c squared minus b squared over 2ac. So essentially we're using law of cosines. So this version, b squared equals a squared plus c squared minus 2ac cosine of b. If we rearrange some terms to get cosine b all by itself, it would be a squared plus c squared minus b squared divided by 2ac equals cosine b. That's the form that was on that other sheet here. So we've got to do a squared plus c squared minus b squared. Okay, so we need 16.61 squared plus 8.6 squared minus b here is 14.5. And divide that by 2 times a times c. So again, all thing in parentheses, 2 times a times c. So cosine of b is 0.489. So b is the inverse cosine of 0.489. And that's 60.75. So we know side A was 16.61 inches. Measure of angle B was 60.75. And then since we know two of the angle measures already, we can add those two. So we have 88.1 and 60.75. And we can subtract that from 180. So 31.15 for measure of angle C. So question 3 might be a little bit easier to see now. You have all three sides. We don't necessarily need to draw this on a triangle, but we still could. We could call it A, B, C. Side A is 19.6, side C is 19, and side B is 22.6. This is a side, 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 like I said, side, side, side. Means we have to use law of cosine to find one of the angles. So just choosing any angle, I'm going to choose angle A. So it's going to be A squared plus B squared plus C squared minus 2BC cosine A. It's this version of law of cosines, or if we want to get cosine A by itself, we can use that form of it. So pretty much a calculator problem here. We're going to have B squared plus C squared. So B is 22.6 and C is 19. So 22.6 squared plus 19 squared, and then we subtract A squared, and A was 19.6. And then we divide that whole thing by 2BC, and since we're dividing by multiple terms, I'm going to put the whole thing in a parentheses. So divided by parenthesis 2 times B times C is 0.568. Then we do the inverse cosine. Of 0.568. We get 55.41 degrees. And we can do a similar type of computation to find the other angle. We can use law of cosines again since we're already on law of cosines. Find angle B, for example. So going back to the formula sheet, if we want to find angle B, we can use this form of the law of cosines, where cosine of B is already solved or already isolated. So cosine of B is A squared plus C squared minus B squared divided by 2AC. So this is 19.6 and 19. So 19.6 squared plus 19 squared minus B squared and then divide that again. Since we're dividing by multiple terms, we're dividing by 2AC. So parentheses 2AC 0.315. So cosine B is 0.315, and then B is going to be the inverse cosine, 0.315. That's 71.66 degrees. And since we know two of the angles now, we can add them together, subtract from 180. So it was 55.41 and 71.66. And then we could subtract that from 180. We get 52.93. for angle C. $52.93. So measure of angle A was 55.41. Measure of angle B was 71.66 degrees. Measure of angle C was 52.93. And question 4. We have A is 51 degrees, side C is 29, and side A is 26. So this is an instance of side-side angle. If the angle had been up here in between where these two sides come together to form the angle, that would have been side angle side, but the angle isn't between the sides, so it's side-side angle. Side-side angle was that special case of the law of sines, where, if you remember, we talked about this back to section 4.1 in the notes. This particular case, side-side angle of law of sines, it's called the ambiguous case. Sometimes we get an answer that doesn't make sense, so there's no such triangle, or we can have a unique solution, or we can have two different values for the angle, or two different values for the side, rather, the missing side. So anyway, it's going to be law of sines, and since we only know one of the angles, we know it's going to involve sine A. So A, which is 26 over sine A, which is sine 51, and the only other side we know is this one. So 29 over sine C. So I'm actually going to flip these around. It's easier to solve an equation when the variable is in the numerator. So I'm going to go ahead and flip these upside down and put sine 51 over side A, and then sine C over 29. Multiply both sides by 29 and we get sine C is 29 times the sine of 51 all over 26. So we need to do that computation now. 29 sine 51. So 29 times the sine of 51. And then divide that by 26 and we get 0.866 or 0.867. So sine C equals 0.867. So then use an inverse sine. And then going back here, inverse sine of that previous answer, 0.866. And call that, I'm going to call it 60 or 60.1. But if you recall, to start this problem, this particular instance of a triangle side-side angle called the ambiguous case, You need to recall from Chapter 3 when we were solving trigonometric equations using inverse trigonometry. We had to we had more than one answer. So you need to recall where else is the inverse sine, or rather, where is the sine positive? Because your calculator is only going to give you an angle that's in the first quadrant, 60.1, but the sine is also positive in quadrant 2. 60.1 is a reference angle of an angle in quadrant 2 if we subtract from 180. So 180 minus 60.1, we get 119.9. So now we got to think, are both of these answers possible, or is one of the angles too big? So remember, the three angles added together in a triangle, all three angles of a triangle can't be greater than 180. The only given angle is 51, so obviously if we add 60, we're good. 51 plus 60 is not bigger than 180, which wouldn't leave any room for a third angle. 119 plus 51, so if we do 119.9 plus 51, that gives us 170. So it's not bigger than 180, so that still gives us a little bit of room for the third angle. So both angles actually work. So angle C could be 60.1, or it could be 119.9. So what we need to do is proceed separately using each individual measurement of angle C. So if angle C is 60 degrees, that's going to give us some different measurements than if angle C is 119.9 degrees, that's going to give us different measurements. So we need to do both of them. So assuming that angle C, let's start with the 60.1. So measure of angle C equals 60.1 degrees. Now we can add those two together to get the measure of angle B. So measure of angle B would be 60.1 plus 51. So 60.1 plus 51, it's 111. If we take that from 180, we get 68.9. So then measure of angle B could be 68.9. Or we could say if measure of angle C is 119.9, then we could add that to 51 and subtract from 180. So it's 9.1. So measure of angle B could be 9.1 degrees. Now we need to find the missing side length B. So B, let's go over back to this case here. This is going to be another law of sines. B over sine of angle B, which in this case is 68.9, equals A over sine A, which is sine 51. And if we multiply both sides by sine of 68.9, so I'm going to multiply over here by sine 68.9, Then I can erase it from over here. So then B equals 26 times the sine of 68.9 over sine of 51. We can do a similar computation for the other angle measure for B. So B equals 26 times the sine. Now instead of 68.9, this could be 9.1 over sine of 51. So just need to plug those both into a calculator. 26 times the sine of 68.9 and then that's divided by sine of 51. I guess 31.21. That would be meters, or 26 times the sine of 9.1 divided by the sine of 51 is 5.29. Meters. So those are the examples, the type of examples you can expect as far as solving a triangle using law of sines or law of cosines. That is from section 4.1, 4.2. Also from section 4.2, law of cosines, were some problems involving finding the area of a triangle in which we don't know the length of the height, so we couldn't use the standard algorithm of area of a triangle, which is 1/2 base times height. So if you notice on the reference sheet, there are some area formulas given, and these would have been also included in the homework for section 4.2. If you have all three sides, then you can use this area formula called Herons area formula. If you know two sides and the angle in between them, then you can use one of these area formulas. So we need to figure out what we've been given here on question 5. So we have triangle, angle A is 150, angle B is 15 degrees, and side A is 7.7. So it said we needed to know, in order to use one of these area formulas, we needed to know two sides and the angle in between. The included angle means angle in between. So we don't quite have that. We need to find another side. That's what we need. So what we're going to actually have to do is use either law of sines or law of cosines, depending which one fits the situation, and find another side. We have to have two sides to use any of those angle area formulas. So let's see what we have here. We have angle, angle, side. That's a law of sines. So we're going to have to find side B. Or, you know what? I'm actually going to find angle C. Well, let's see. Let's find angle C first and then decide what side we're going to find. So angle C is going to be easy to find. We just add the two given angles. So we have 150 plus 15, that's 165. If you take 165 from 180, you get 15. So angle C is a 15-degree angle. So at this point, we can find either of the two sides. It doesn't matter. We could either find side C here, or we could find side B. Just because I started with side C, I'm going to stick with it. So side C over sine of angle C is the length of A over the sine of angle A. Multiply both sides by the sine of 15. So now we get the measure of, or the length of C is 7.7 times the sine of 15. Divided by the sine of 150. We get 3.99. So now we have what they required for that area formula. We have two sides here and the angle in between them. So I'm going to use side A, side C, and angle B. So I need to find one of those area formulas that includes side A, side C, and angle B. And this is one here, 1/2 AC sine B. So area equals 1/2 AC sine B. So 1/2 times 7.7 times 3.99 times sine of angle B is 3.98. And the units here is kilometers squared because it's an area. Now for question 6, we have 3 sides of a triangle given. So if we have 3 sides, we can use Herons' area formula, which is first we need to know this value of S. It's half their perimeter, or called semi-perimeter. And then you apply that into that formula. So first thing is to add all 3 sides. And then divide it by 2. So we have 9.8 plus 8, that's 17.8, plus 10, 27.8, divided by 2. That's 13.9. And then the area formula was the square root of S times S minus A times S minus B times S minus C. So 13.9 minus 8, and then 13.9 minus 9.8, and then 13.9 minus 10. So 13.9 subtract 8, 5.9. 13.9 minus 9.8 is 4.1. And 13.9 minus 10 is 3.9. So we need square root of 13.9 times 5.9 times 4.1 times 3.9. I think it was 3.9, yeah. 36.21. What do we have, kilometers again? Kilometers squared. That ends, at least at this point, problems from chapter 4. We now swing, well, no, I stand corrected. These vector problems were from 4.3. We haven't gotten to chapter 5 yet. These are vector problems now from 4.3, magnitude and the direction angle for the vector. Magnitude is just Pythagorean's theorem. So let's see. Whoops. Get square root here first. There it is. And we had 9 squared plus 40 squared. It's 41. So the magnitude there is 41. And then the direction angle for a vector, we're going to call it theta, was the inverse tangent So it was the inverse tangent of 40 over 9. And that's 77.32. But you need to recall now, inverse tangent of b over a, since b over a is positive, we use absolute values. That's always going to give you an angle in the first quadrant. But if you think about where this vector is, -9, -40, that's in the third quadrant. So this angle here, 77.32, is a reference angle for an angle in the third quadrant. So we need to add that to 180. And we get 257.32. So the actual angle is 257.32 degrees. And then the magnitude of vector B was 41. Question 8, asking us to do the same thing, it's just a different notation. It's the unit vector form, I and j, but we can still find the magnitude. It's going to be the Pythagorean theorem again. 8 squared is 64, 3 squared is 9, so we need the square root of 73. It's 8.54. And then the direction is the inverse tangent. If we're going to do absolute value, inverse tangent at 3/8 and 20.56. And then we need to consider where that vector is pointing. It's pointing off into the second quadrant. So this is just a reference angle of an angle that's in the second quadrant, which means we need to take this angle away from 180. So 180 subtract that angle gives us 159.44. So we have the magnitude there and the angle of the vector. So question 9, this is from, again, section 4.3. The target here, the learning target, is performing operations on vectors. The resultant vector just means, once you perform these operations, the resultant vector is what is the vector that results from performing these operations. So first I'm going to do -4 times a. If I multiply all the components of angle A by -4, I'm going to get positive 36 and a -4. And then if I do 10 times V, that's going to give -120 and -100. Now all I got to do is subtract these. And you subtract horizontal components, so 36 minus 120, rather 36 minus -120, so that's going to be positive, because we're adding. That's 156. And then -4 minus -100, again, subtract a negative is the same as adding, so it's -4 plus 100, which is 96. So we need to find a dot product for question 10. This is the learning target at the end of unit 4.3 or lesson 4.3, which is dot product and finding angle between two vectors. So the dot product is the product of the horizontal components. So -6 times -2, and then you add that to the product of the vertical components. -4 times 9, so this is 12 plus -36, which is -24. So that's the dot product. Now the angle between two vectors was one of those formulas included on our formula sheet. The angle between two vectors is found using the cosine. the numerator is the dot product of the two vectors, which we've already found. Then the denominator is the product of the two individual magnitudes. So cosine of this, the angle in between the two vectors, is going to be the dot product divided by magnitude of u multiplied by the magnitude of v. So I'm going to go ahead and find the magnitude of u. That's going to be the Pythagorean theorem. It's just the square root of -6 squared plus 4 squared. So -6 squared is 36, and then -4 squared is 16. 36 plus 16 is 52. Now the magnitude of v is the square root of 2 squared plus 9 squared. So -2 squared is 4, 9 squared is 81. So this is the square root of 85. So the cosine is going to be the dot product, which we already found to be -24. And then it's the square root of 52 multiplied by the square root of 85. So we got to turn this into a number on a calculator and then take the inverse cosine of it. So I'm going to do the square root of 52 multiplied by the square root of 85. And then -24 needs to be divided by that value. And then we need to take the inverse cosine of that value. And we get 111.16. So the inverse cosine of -0.36 was 111.16. So we have the dot product and the angle between the two vectors. Question 11, 12, 13, and 14. These are the questions now from Chapter 5, complex numbers in trigonometric form, and using de Moivre's theorem to find the powers of complex numbers or the roots of complex numbers. So multiplying two complex numbers together when they're in trig form is pretty easy. You multiply the numbers in front, and you add the angles. Okay, let's see, pi over 6 and 5 pi over 4. We need to get a common denominator of 12. So that's going to be 2 pi plus 15 pi. That's going to be 17 pi over 12. But it specifies here that the answers need to be in standard form. This answer here is in trigonometric form, so we need to convert that back into standard form. So if you remember, CIS is just the abbreviated form of cosine plus I sine. So this is 6 cosine of 17 pi 12ths plus 6I times the sine of 17 pi 12ths. So we need to figure out 6 times the cosine. And now I need to get back into radian mode. So 6 times the cosine of 17 pi over 12. And that's negative 1.55. Now 6 times the sine of 17 pi 12 is negative 5.8. So this would be the standard or rectangular form. Now, dividing complex numbers when they're in their trigonometric form uses the same algorithm. So we've got 3 CIS 5 pi fourths divided by 2 CIS of pi 6. What we do is divide the coefficients and then subtract the angles. So see, 5 pi fourths, that was 17 pi 12ths. And then pi 6 is 2 pi 12ths, so 15 pi 12ths minus 2 pi 12ths is 13 pi 12ths. But again, that's the trigonometric form of this. So this is 3/2 times the cosine of 13 pi 12ths plus 3/2 I sine of 13 pi 12ths. So we need 3/2, which is 1.5 times the cosine of 13 pi 12ths. It's negative 1.45. And then 3/2 is the sine of 13 pi 12ths. It's negative 0.39. Okay, and then De Moivre's theorem says if we have some complex number in trig form, then z to the power of n is r to the n, and then you multiply the angle by that power. So what we need to do is convert this complex number into trigonometric form first, and then we can apply De Moivre's theorem. So the value of R is, using Pythagorean theorem, it's kind of like finding the when we're back in section 4.3, the magnitude of a vector. So 1 squared is 1, square root of 3 is square root of 3 squared is 3, 1 plus 3 is 4, so square root of 4 is 2. And then the angle is inverse tangent of b over a. So the inverse tangent of the square root of 3 let's go back into degree mode. So inverse tangent of the square root of 3 is 60 degrees. And then we need to consider, where is this complex number graphed on the complex plane, and it would be in quadrant 1, which is where that angle is. So we take that as our angle. So the trig form of our complex number is 2 CIS 60. So then Z.
Okay, so if we now want to find Z to the 8th power, we do this formula here. So 2 to the 8th CIS 8 times 60 degrees. 2 to the 8th power is 256, and then 8 times 60 is 480. So we just need to figure out now what cosine of 480 and the sine of 480. That's negative 128. That's 221.7. Okay, question 14. Now we're using De Moivre's theorem to find roots. So it's slightly different than the version of the theorem that we just used to find a power. So if we want to find 5/5 roots of 32, and we have Z equals 32, that's our complex number there. And the formula of the theorem that we use in the textbook is W for the root is equal to R to the 1 over N CIS. Then we need the angle plus multiples of 360. And since we're doing 5/5 roots, we're going to have k equals 0, 1, 2, 3, 4. And for 5/5 roots, we're going to have n equals 5. Now, first what we need to do, complex number in trigonometric form. Here we have it written in standard form. So luckily though, since it's just a whole number part, or the real part of the complex number, if we were to graph 32 on the real and complex axes, 32 would be right here on the real axis, and the angle there would be 0. And the distance there, the r value, would be 32, so it's just 32 CIS 0. So we need 5 instances now of this formula. We need a root for when k equals 0. So this is going to be 32 to the 1/5. And we're going to have 0 plus 360 times 0 over 5. And then CIS. And now we need to figure out the angle. So remember, theta was 0, and then we have 360. In this case, k equals 0, divided by 5. This value here turns out to be 0 divided by 5, which is 0. So this is 32 to the 1/5. That's actually, which is 2. And this is cosine 0 plus I sine 0. Sine 0 is 0. Cosine 0 is 1. So we get 2. We just need to repeat this a couple more times for k equals 1, 2, 3, 4. So now we do 32 to the 1/5. Now we have 0 plus 360 times 1 over 5. 360 divided by 5 is 72. So this is 2 CIS 72, which is 2 cosine 72 plus 2I sine 72. So we need 2 times the cosine of 72. That's 0.62. And then 2 times the sine of 72. That's 1.9. case for W2. So this is 32 1/5. So this is now 720 divided by 5. It's 144. So we've got 2 cosine 144 plus 2 2i sine 144. So 2 cosine 144 is negative 1.62. And 2 sine 144 is 1.18. Now we need W3. So 32 to the 1/5, CAS 0 plus 360 times 3 divided by 5. So that's 216. So this turns out to be 2 CIS 216, which is 2 cosine 216 plus 2i sine 216. So we figure out 2 cosine 216 negative 1.62 and then 2 sine of 216 negative 1.78 or negative 1.17. And we'll round that up to 1.18. And as we talked about in class, complex roots always come in conjugate pairs, always. These two, for example, you can see are conjugate pairs. So the only one we're missing then is the conjugate pair for that one. And since there's only one left, we can make the conclusion that that last root, W4, would be the conjugate pair of this one, so 0.62 minus 1.9i. So there's the last one. There's the fourth one, third one, second one, and first one.
All right, question 15 and 16. These are applications. And looks like we have a typo there. I apologize. That should be the. All right. Two ships left port at the same time. This is one of these heading questions. The first ship rather, traveled at a heading of 318 degrees. So remember, headings are in relation to 0, so 318 would be right about there at 18 miles per hour. And the other ship left the same port at a heading of 198. So leaving from the same port, this would be 90 degrees, this would be 180, so 198. Be right about there. And that is 22 miles per hour. Let's clean this up a bit. Find the distance between the two ships after 10 hours of travel. Okay. Well, 18 miles per hour for 10 hours is 180 miles. So this ship has gone for 180 miles in this direction. And then 22 miles per hour times 10 hours would be 220 in this direction, so it's a little bit longer. And it wants the distance between those two ships. Well, we can figure out this angle right here using the headings. So we superimpose an axis system onto this. This first ship had a heading of 318 degrees. So if we take away the 270 from 318, that leaves us with 48 degrees.
Okay, so we have this gap then is 48 degrees. Now this heading there, if you remember, was 198 degrees. Finishing off that angle up there to the x-axis would be 270 degrees. So the gap there would be the difference between 270 and 198. So that's 72. Degrees. So what I want then is the measure of that entire angle. So 72 plus 48. That's 120. So we have a 120-degree angle there. And what we need to do then is figure out this distance here. Now we've got a side, two sides, and the angle in between them. So that's an example of side angle side triangle. To find missing measurements on a side angle side triangle, remember we need law of cosines. So if we were going to label this as A, B, and C, then what we're looking for is side A. So we would need this version there of law of cosines. That's 180 squared plus 220 squared and that's just one big computation we can do on a calculator. So a squared equals 120,400. If we take the square root of that, get 346.99. And this is in terms of, let's see, miles. So 346.99 miles. Okay. So question 16 from section 4.3, an application of vectors is work. So the formula for work is the magnitude of the force multiplied by the magnitude of the displacement multiplied by the cosine of the angle between the force vector and the displacement vector. So if we have this box, and it's going to be dragged 15 feet, then that's the displacement vector here. But a force of 75 pounds is being applied at an angle of 32 degrees to the displacement vector. So the magnitude of the force is 75 pounds. The magnitude of the displacement vector is 15. The angle between them is 32, so 75 times 15 times the cosine of 32 is 954 foot-pounds.